Welcome everyone. I'm Tulasimohan Molli. I'm going to talk about our work on Chang's lemma type bounds of Boolean functions. This is joint work with Sourav Chakraborty, Nikhil Mande, Rajat Mittal, Manaswi Paraashar, and Swagato Sanyal. So the talk is divided into three parts. First, I'll talk about some definitions which are needed to set up Chang's lemma. Then I'll talk about Chang's lemma, similar bounds, and some other improvements to these bounds. And in the final part, I'll talk about some type functions which match these bounds. So let me begin by recalling some definitions from Fourier analysis of Boolean functions. For the purpose of this talk, a Boolean function is a function from -1 to n to -1. So every Boolean function can be expressed as a linear combination of these parity functions, and the coefficients are called Fourier coefficients, and this representation is unique. So for each alpha in 0 to the n, this chi alpha is defined as product of xi's for where alpha is 1. These Fourier coefficients satisfy this nice property that when you square them and sum them, they add up to 1. Let's look at some examples of Boolean functions and therefore expansions. So let's begin with AND function. AND function takes the value -1 on the all -1 input, and it takes the value 1 on the every other input. So AND function on 3 bits has the following Fourier expansion. The thing to note here is that f hat empty, or the empty Fourier coefficient, is close to 1, and every other Fourier coefficient is close to 0 in absolute value. This would be true for AND in general. Another interesting Boolean function is this addressing function. So addressing function is a function on log t plus t bits. It has two kinds of inputs. One is the address inputs, and the other is the target inputs. Each target input has an address of log t bits. Right? On an input x comma y to the addressing function, the function just outputs the entry in the address y. So addressing function has the following expansion. It can be written as sum over b 0 to the t indicator of b times xp. So this indicator function takes the value 1 when y equals b, and it takes the value 0 otherwise. So for any given y, only one of these indicator function is going to fire 1, and all other indicators are going to fire 0. So you can convince yourself that this expression is indeed computing the addressing function as we defined before. This indicator can be written as this polynomial, and when you expand this polynomial, you get this expansion for the addressing function. Again, the thing to note here is that the absolute value of all the Fourier coefficients here is 1 by t. So yeah, again, another interesting function is the inner product function. As the name suggests, if x and y are thought of as inputs from 0 to the n, this is just the usual inner product over f2. Yeah, if x and y are from -1, it translates to this function. And the inner product function this is the Fourier expansion of the inner product function. And the thing to note here is that all the Fourier coefficients are 1 by 2 power n in absolute value. Yeah, such functions are called bent functions. Okay. Now let's look at some Fourier analytic measures. For a Boolean function which is written as summation f hat alpha chi alpha, the support is defined as the collection alpha such that f hat alpha is non-empty. Okay. And sparsity is defined as a size of the support, or the number of non-empty Fourier coefficients, non-zero Fourier coefficients. Dimension is defined as the dimension of the space spanned by the support, and max entropy is defined as the inverse of the smallest Fourier coefficient in absolute value. Max rank entropy is denoted by k double prime,
is defined as the smallest t, such that if you look at the coefficients which are greater than 1 by t, they span the support, they generate the support. And lastly, weight is defined as the fraction of minus ones in the truth table of F. Yeah. These are some interesting Fourier analytic measures. We'll, in the next slide, we'll take an example of some functions and compute each of these measures for those functions. Then I guess the definition will be a bit more clear. Okay, so we'll start with the AND function. Like I said before, the AND function, the empty Fourier coefficient is close to 1 and every other Fourier coefficient is close to 0. And yeah, all the Fourier coefficients are non-empty. So the support is everything, which is f2 to the n. And so the sparsity is the size of support, which is therefore it is 2 power n. And dimension is the dimension of that space. The dimension of f2 to the n is n. And max rank entropy is the inverse of the smallest Fourier coefficient in absolute value. So the smallest Fourier coefficient in absolute value here is 2 by 2 power n. So the inverse of that is 2 by 2 power n minus 1. Okay, and again, max rank entropy is the smallest t, such that if you look at the Fourier coefficients which are greater than 1 by t, they generate the support. If you take Fourier coefficients which are greater than 1 by 2 power n minus 1, they generate the support. And if you take if you take t to be any smaller, then 1 by 2 will be 1 by t will be larger than 1 by 2 power n minus 1, and
that set is not going to generate, and that set is going to be empty, and it's not going to generate the entire support. And lastly, the weight of AND function is 1 by 2 power n, because I mean, you can see it in many ways, but one easy way to see it is that there's only one input, which is outputting -1, and out of the 2 power n inputs, so the fraction of inputs where it's -1 is 1 by 2 power n. And our next function is the addressing function. So as we've seen before, this is the Fourier expansion of addressing function. There are each Fourier coefficient is 1 by t in absolute value. Okay. Now let's see how many terms are there in this expansion. So this b is summed over 0 onto the log t. So b is sum of t terms, and each term is indeed again a sum of t terms. So there are total t square terms in this summation. So the sparsity of ADT is t square. So, and the function is dependent on t plus log t bits. So the dimension is t plus log t. And again, recall that max rank entropy is the smallest Fourier coefficient, inverse of the smallest Fourier coefficient in absolute value. So it turns out to be t here. And max rank entropy is the smallest threshold t, such that Fourier coefficients greater than 1 by t generate the support. Again, here it turns out to be t, and weight of addressing function is half.
Okay, now let's get into the definition of Chang's lemma, statement of Chang's lemma. So in order to do that, let's define this quantity support t. Support t is just the collection of alpha such that f hat alpha is greater than this threshold t. And RT is defined as dimension of the space spanned by the support t. If t is chosen such that all non-zero Fourier coefficients lie in support t, then RT will turn out to be R, and support t will turn out to be support. Okay, what is Chang's lemma saying? Chang's lemma gives an upper bound on RT in terms of this threshold parameter and weight of the function. The bound is the following. Chang's lemma says that RT is upper bounded by t square delta square times log 1 by delta. Right? And this holds for every threshold t. And yeah, so what we study is Chang's lemma for these three interesting parameters,
which are k, k prime, and k double prime. For example, when you put t equals k, we get the bound that RT is less than k squared delta squared log 1 over delta, and so on. We get 3 bounds for each of these parameters. Okay. Okay. There are other bounds which are like Chang's lemma bound. They also give a upper bound on rank. One interesting such bound is bound by Swagato Sanyal, one of our co-authors of this paper. He showed that rank is upper bounded by square root k log k. Another interesting upper bound on shown by Chakraborty et al. They actually showed that degree 1 L1 norm of degree 1 Fourier coefficients is upper bounded by 4 log k. From this, it implies that with a little bit of calculation, it implies that rank is upper bounded by 4 times k double prime log k. These are the 2 Chang's lemma type bounds which are known in the literature before. Now let's jump on to our results. So what we showed is we improved these 2 bounds by Sanyal and Chakraborty et al. Our results improve on both the previous results. So firstly, we showed that R is less than square root k delta log k, which is a better bound than square root k log k because square root k delta is always less than square root k. And we also improve on the bound of Chakraborty et al. By showing that R is less than order delta k double prime log k by throwing in a delta term here. Also, we also observed that delta is greater than k by k double prime, which implies, with a little bit of calculation, it implies another bound on R in terms of k prime delta and k. Note that the first bound is on R is in terms of k and delta. The second bound is in terms of k double prime delta and k. And the third bound is in terms of k double prime delta and k. Okay. Okay. Let's here's a comparison of the R bounds to that of Chang's lemma bounds. So for a fixed R and k, if you plot delta versus k prime, these are the plots of the 3 bounds. One is the Chang's lemma for the threshold k prime. Another is the improvement of Sanyal. And the third one is our observation that delta is greater than k by k prime square. The blue is the observation, green is the improvement of Sanyal, and red is the Chang's lemma bound. As you can see from this picture, the green line and the blue curve together subsume the red curve. So in this sense, our bounds are better than the Chang's lemma bound. And secondly, if you look at bounds in terms of k double prime, again, the red curve is the Chang's lemma bound. The blue curve is the bound, which is the improvement of Chakraborty et al. And the green line is the improvement of Sanyal et al. Here, what we have is that for very small k double prime, Chang's lemma still does better than our bounds, but everywhere else, our bounds dominate Chang's lemma. Okay. Now let's get into some of the proof ideas of one of our theorems. So yeah, so theorem 1 states that R is less than square root k delta log k. So the proof of this theorem is inspired by Sanyal's proof. So it begins with the observation that Fourier dimension is nothing but the non-adaptive paridation tree depth. So in order to show upper bounds on Fourier dimension, it's enough to construct shallow non-adaptive paridation trees for F. Okay, that's what we do. A crucial ingredient in constructing non-adaptive paridation trees is this lemma by Chang et al., which says that for any Boolean function, there is a small collection of parities such that a setting of them which makes it 0. The small is again quantified by 3 square root k delta. Let's look at the algorithm for producing non-adaptive parity relation trees. Given we're given a Boolean function, we want to output a bunch of parities such that when you query these parities, for each setting of these parities, the function becomes a constant. So what we have with us is the Chang et al. Lemma, which says that, which gives us a bunch of parities, such that one of the settings makes it a constant. Okay, so how do you use it? So first we start with f, apply the Chang's lemma, and get a bunch of parities, gamma 1. Okay, and query these parities and form a complete binary tree, and look at all the functions in this level, in the second level. Among those functions, pick the function which has the smallest delta by k ratio. On let's say that is this green function. On that function, apply Chang's lemma and get gamma 2 from Chang's lemma. Again, on all functions in level 2, query gamma 2, and you get a bunch of functions in level 3. And in level 3, pick the function which has least delta by k ratio, and you again apply Chang's lemma on that. You proceed this way. At some point, all the functions in some level become constants. That's when you stop. And the claim is that these parities which you have collected using Chang's lemma at each level, if you put them all together, they're not too many in number. That shows that that is the non-adaptive parity relation tree algorithm, and this analysis is non-trivial, and I'm not going to cover now, but you can check it in our paper. Okay. And yeah, now moving on to the third part of the talk, which is, are these bounds achievable? We have 3 bounds. One is a bound on R in terms of k and delta, a bound on R in terms of delta k double prime and k, and a bound on delta in terms of k and k double prime. Okay, and yeah, let us formulate this question a bit more formally. Normally, in order to show that a bound is tight, you generally exhibit one set of parameters where this is an equality. But what we show is slightly stronger. We show that for most or for almost all admissible parameter values of R, K, and delta, this bound is we show functions which satisfy this bound and have these parameters. Okay, what do I mean by that? Let's okay, so this is the graph which plots the Chang's lemma curve, and this is the Sanyal's, this is bound from theta 1, and this is the observation. So what we are going to show is we are going to exhibit functions given an R, K, and K prime. We are going to give a function which has dimension R, sparsity K, and max entropy K prime, such that delta is given by R square by K log square K. The formal statement is that for all admissible RK and K prime and delta, such that R is equal to square root K delta log K, we show Boolean functions whose sparsity is K, dimension is R, max entropy is K double prime, weight is delta, and moreover R is square root K delta log K. How do we do that? So yeah, the function, we obtain this function by taking the addressing functions and modifying it a little bit. So we're going to take the addressing function, and yeah, so we're not going to replace all target bits with ands of same arity. So one of the addressing bits we are going to replace with a larger and every other addressing bit we are going to replace with ands of same size but smaller size. These are all on independent sets of variables. Turns out if you write the Fourier expansion of this and compute the measures, interesting, a rank of this such a function turns out to be roughly t log t prime plus log a. Sparsity turns out to be roughly t squared times t prime. Max entropy turns out to be a times t. Max rank entropy turns out to be a times t, and weight turns out to be 1 over t prime. Now you can verify that firstly that these numbers satisfy this equation r equals square root k delta log k. And moreover, since here we have three independent variables rk and k prime, three free parameters, and here you have t prime and a. So by tuning t prime and a, we can make these quantities t log t prime, t square t prime, at to be whatever rk and k prime we want. And similarly, we want to show that given any r, k prime and delta, we want to construct a function such that delta is equal to k by k prime square. Again, this is, we do this again by taking the addressing function and again modifying it. But this time, what we do is the target bit, each target bit is replaced by this gadget. Previously, we replaced target bits by ands. Now we are going to replace target bits by and of inner product. If you set these arities appropriately, we can obtain a function which matches as bound delta equals k by k prime square. And lastly, we want to show tightness of this k prime curve, which is delta equals r by
k double prime log k. So tight function for that is constructed by taking the addressing function, and this time what you do is it's like replacing target bits with ands, but except the first guy, the first and is not a simple and. The first variable, what you do is you multiply it with and of a bunch of variables starting from the second block. Starting from the second block, pick up the first p variables and take the and of them and multiply that with the first variable and take the and of all the things in the first block.
That's what is going to that is what you're going to put here in the first block. Turns out this gives us functions which match this bound r equals k double prime delta log k. For all the functions we have seen before, k prime is equal to k double prime. And this is a function where you'll notice that k prime and k double prime are different. Yeah, those are the three tight functions. And thank you.